Hey everyone, today we'll be presenting our work for the text VQA shared task titled Graph Relation Transformer, Incorporating Edge Relations into the Transformer Architecture. In this work, we tackle the text VQA task in which the questions are basically about the text in images. So this requires a model which can read and reason about the text in images. In this work, we build upon the 2020 text VQA task baseline model, which is the M4C model. The M4C model is a multimodal transformer-based model with iterative answer decoding and appearance-based features for the OCR text.
Onto our proposed approach. We noticed that the M4C model often struggles with questions that involve reasoning about spatial relations between objects in the image, which include both visual objects and OCR text objects. Firstly, the M4C model uses the transformer architecture, which is implemented such that only point-wise features for each object are incorporated. And you can see some of M4C's features listed in the node features box. Our experiment involves incorporating edge-wise features between these objects into the transformer. For example, relative visual appearance, spatial relation type, spatial position, and the modalities of the two objects connected by the edges. By giving the model access to these relational features, our experiments show that performance on the text VQA task improves. So then how do we inject or incorporate these relational or edge features in the architecture? An important characteristic of transformer architecture is that its self-attention module already implements graph computation that does pairwise computation between every object, and it does so using their respective point-wise features. So in fact, the only missing part is that there's no natural place in the existing architecture to incorporate the edge information. The key idea of the graph relation transformer is where to incorporate the edge features. For this, we focused on the multi-headed detention module of the transformer. The way that this module works is that for some object I, the key of some object J determines how much attention I pays to J, i.e. how relevant J is. So one of our ideas is to fuse the edge features E into the node features X at this key with a fusion function phi. And possible choices of phi are the concatenation or addition functions. And so the idea here is that we allow object J's relevance for object I to depend on the edge information. Next, the other possibility is to fuse the edge features at the value. Even though the method is exactly the same, the intuition is different. In the transformer, the value affects how the information in object J affects the representation of object I after attention. So, fusing the edge features E with the node features X at the value, we allow the influence of object J on object I to be dependent on the edge. In our experiments, we explored fusing at the keys only, values only, or both.
The quantitative results. Here we see that the graph relation transformer does perform better than the LoRa and the M4C architectures, and this is seen across both the validation set and the test set. One thing to note here is that all of these models were trained without any optimizations, such as joint training with the STVQA dataset or using improved OCR modules.
To determine the best fusion function, we conducted experiments with different fusion functions, concatenation or addition, in different fusion locations at the keys, values, or both. Here we see that the best setup is reached by the add fusion function for the values only location. And this setup produces the results reported on the previous slide. Take note that these models were trained to 5,000 iterations and not to convergence purely for comparison purposes. We additionally conducted an ablation study to understand the impact of specific edge features on model performance. Here we see our model trained with all edge features does perform better than the M4C baseline. We also see a boost in performance when removing the visual similarity edge feature. This feature was removed for our best model setup that we report on. We also see a cluster of lower performing models when removing the other three spatial edge features. We believe there to be valuable information in these spatial edge features, which is where the drop in performance comes from.
Injecting edge features does allow the model to better reason about the spatial relationships among the different objects in the image. On the other hand, the OCR token accuracy remains to be the biggest bottleneck, resulting in most of the errors that we see. Thank you.